Okay, so last week we were discussing this conservation laws. Especially there was one point that was kind of, I think, confusing for you. And you see, whenever you are talking about conservation laws, we are basically talking about an equation of this form. d by dt, some quantity f, or let's say the integral over some given volume of some quantity. This should be equal to minus the integral over the surface of that thing. Or let us write it in this form, ji ds dai. This is what we call the conservation law. You can just get rid of the integrals if you want. This is the same thing as the time derivative of one of those things, the number, or so-called the density, should be equal to minus the divergence of the other quantity. Or since we have three of them, we can write it as the summation over the three components of their derivatives. So whenever you see such a relation, that means there is a conserved quantity in that system. Now, of course, this rho and j can be different things. Their interpretation is a completely different story. But for example, this rho can be let's say, the charge density. Then we say that this is the charge current. This rho can be the energy density. Then this j is the energy current. Or this rho can be the the linear momentum in the x direction, the density corresponding to the linear momentum in the x direction, then this would be the current of linear momentum in the x direction. And of course, if you are talking about the momentum, vectors like momentum, they have three different components, so x, y, and z. For each x, y, and z, you have this vector. For each component, you have the x component, there's a vector that describes its flow. You have the y component, you have a vector that describes its flow. For the z component, you have a vector that describes its flow. So this thing over here that comes over here, it looks like a vector, not exactly a vector. It has some common properties as vectors. And in fact, it is what we call a generalization of a vector. So you see, up to now, what we have seen as mathematical objects, we have seen numbers that we call scalars. We have seen vectors. Basically, if you choose your coordinate axis, the vector you can represent as just three numbers. And they have certain common properties. Whether you have a number or a vector, you can multiply them by numbers. Whether it's a number or a vector, you can add them. So these are the common things about the scalars and vectors. And we basically generalize it. And we call all of these, numbers and vectors, things that you can multiply with numbers, things that you can add them, and things that you can write as a bunch of numbers once you choose your coordinate axis. And if you choose your coordinate axis differently, they will probably look different. The numbers will look different, but nevertheless, the initial set of numbers and the final set of numbers, they have some relation between them. Just like think in terms of the vectors. So let's say I have this vector. If I choose my x, y, and let's say 2 dimensions, the x-axis and the y-axis, this vector has some x component and some y component. If you choose this as your x-axis, and then this as your y-axis, the perpendicular direction of it, x and y components will be different, but they are related to each other. So if you know the x and the y components of a vector in this coordinate axis, you can determine the x and the y components in this coordinate axis. So look, we said that vectors are just three numbers, but they transform in a particular way. And we call these two things, scalars and vectors, that have these common properties. They are also what we call tensors. Scalar is a tensor. A vector is a tensor. And of course, we define other quantities like this one, j, corresponding to momentum. We call that one also a tensor. So it's what we call tensors are in a sense, generalization of vectors. This is all you need to know about tensors. I mean, tensors as a subject itself, it's a deep subject. When you, well, in principle, you should have learned it in when you take, you should learn it when you are taking linear algebra, 216, 260, but I don't think they cover it in the 260 course. Now, I strongly suggest you in your life as a physicist to learn linear algebra. I'm not talking about the matrices, diagonalization, etc., but what linear algebra actually means. And then it will make more sense to you what tensors are. But for the purposes of using in this course, think of tensors as just generalization of vectors. You see, vector is a number is a quantity with zero-dimensional information. A vector is a quantity with one-dimensional information. A tensor of second rank is a quantity which will have two-dimensional information. And a tensor of rank 3, let's say, it will be a number with three-dimensional information. What do we mean by this information of two dimensions, three dimensions? Let's look at this example. Of momentum. We were talking about the momentum conservation. We said that, okay, if we talk about the x component of momentum, that is one direction information. We are talking about the component of momentum in one direction that we chose to be x. That flows in some other direction. It doesn't have to flow in the x direction, so it flows in some other direction. So whatever appears over here should contain those two direction information. Which direction of momentum are we talking about? And which direction does it flow? So that is why we call it a rank 2 tensor, because it has two directional information. Knowing this much about tensors for our purposes is enough. Of course, I do strongly suggest you that learn linear algebra well. And by learn linear algebra, I'm not talking about matrix multiplication, diagonalization, etc. I mean, when I was a student, I took a linear algebra course that was like 2 semesters, and we only saw the matrices at the end of the second semester. And it was something like, okay, there's also these things that you should be aware of. They are not really so much relevant for linear algebra, but know them. So there's a whole field of linear algebra where you learn these matrices, vectors. No, not matrices. Matrices is just one part of it. What does a linear operator mean, etc. What are tensors? Of course, that's not urgent. Just make your plan so that if you want to be, especially if you, even if you want to be experimentalist, you should have an understanding of linear algebra, not just knowing the manipulations of matrix multiplication, diagonalization, etc. Now, any questions on this one? Because we will be switching to some other subject. On Wednesday, we will have a recitation. I'm planning to do some examples on this linear angular momentum conservation, etc., some explicit calculations. But if you don't have any questions, we will start our new subject. Here. Well, what's the divergence of a vector field? You just take its j component, take its derivative with respect to xj. This is the j component of something. For a given I, this is the j component of something. I'm taking its derivative with respect to xj. So that's the definition of divergence. So that's why I'm just jumping it over here. For each I, again, I said, okay, it can be, we might be talking about the x component of linear momentum, y component, or any component that you like. For that component, this is the divergence of a vector. So once we know this, then that is the proof of conservation, because we are basically expressing everything in terms of that first line as our first line appearing over there. So there's some quantity that we are integrating over our volume. We are looking at how it changes in time. So there's also a time dependence over there. We are looking at how it changes in time. And if it's changing in time, that change can completely be described as a kind of a flow over the surface only. It's not because some of that quantity is disappearing inside my volume. It is passing through my surface. So that is why it should be here, if we write the volume integral over here, it should be a surface integral over the surface of that volume.
Şimdi normalde bunun konserve olması için değerinin sıfır olması gerekmiyor mu?
Depends on what you mean by conservation. In general, what we mean by conservation is that some quantity doesn't change, the total of a quantity doesn't change in the universe. Okay, that is, let's say, conservation. Okay, let's look at this one. This example, look at the first line. Well, if we are talking about the universe, then our volume is the universe. Then this surface is the surface of the universe at infinity. All the fields are zero at infinity. There is nothing at the boundary of the universe at infinity. So that is zero anyway. So this equation already contains your description of the conservation. But in general, we don't want just conservation. We want local conservation. You see, this conservation in the universe means that something might disappear at this point and it might appear in the next galaxy at the same instant. That is still conserved. But we know that that doesn't happen. Conservation is a local quantity. If something disappears at this point, at a given instant, we know that at the next instant it is nearby. It cannot go to the Andromeda galaxy. Just as at the next instant, it's just at the next point. So that local conservation is expressed in this form, which basically means that if we have a volume, if the quantity in that volume changes, and if the quantity is conserved, the only thing that might happen is that that quantity has left our volume. It passed through the surface. So that time change, we should be able to express it in terms of a surface integral. Because if it changes, it should be because some of that quantity passes through the surface. Not because some of it just disappears here and appears in the next galaxy. Well, I will be using the term conservation. This is the statement of conservation, but in some places you will see that it's the local conservation. Yes, yes. Because you see, when we are defining the force, the pressure, okay, Tij is the flow of momentum per unit time, per unit area. So it should be flowing through this surface. So we don't really care about the flow parallel to the surface. We are interested in the flow perpendicular. We want the flow crossing this surface. That is why we put one of those ends. The second n is, okay, this is a flow. If you have this vector, let's say, it is flowing through the surface. So we have this momentum in this direction. It passes through my surface. So it exerts a force on this surface in this direction. What we want is the perpendicular component of the force, because that is the definition of pressure. The pressure is the perpendicular direction of the force per unit area. So one of it, if this is the vector, this vector might be flowing, let's say, in this direction. We only take the flow perpendicular to the surface. That's why we are multiplying it. We are taking the scalar product with the vector perpendicular to the surface. That is our n. The second thing, we don't want the force in this direction. We want the component of the force perpendicular to the surface. That is why we are taking the second scalar product. The first scalar product gives me the force acting on the surface. The second scalar product gives me the perpendicular component of the force acting on the surface. And that is what we call pressure.
Peki scalar product'ı alırken bir işlem önceliği var. Şimdi hani iki tane normal vektör var sonuç olarak. İki normal vektör kendi arasında bir scalar product olursa anlarsın.
But you see, this is the definition of how we are defining that scalar product. This is what we call the pressure. Well, of course, this is assuming that all that electromagnetic field is absorbed by the surface. You see the way, I mean, it doesn't really weigh which is I, which is J, because this is symmetric, this is symmetric. But the component of N is multiplied with one index of T, and the other N is multiplied with the other index of T. Sometimes we also write this in this form, N times T times N. This also specifies the direction.
Ben de şimdi IJ2 konferansı hangisi momentum yani hangisi momentum?
It doesn't really make any difference. Because since it is symmetric, we don't really care. I mean, you can say that I is the direction of the momentum which is flowing in the J direction.
Hocam şimdi bu tüm radiation yüzey tarafından emildiğini mi gösteriyor?
No, it doesn't. I mean, what we are actually, you say, what is T? It is the flow of momentum. So let's say you have this surface, this hypothetical surface. And so the momentum is flowing through this surface. So let's say if this is the surface of an object, and all this electromagnetic field is absorbed by this object. So basically, since this is the flow of momentum in this direction, well, what is force? Force is the rate of change of momentum. Well, this is the flow of momentum, rate of the flow of momentum. That is the momentum passing through a surface per unit time per unit area. So if all this momentum is absorbed by my object, in that case, this will be the pressure, or this will be the change in momentum of my object, and hence the force acting on my object. It might be that you have, I don't know, some mirror over there. You send some electromagnetic radiation, electromagnetic wave, it bounces back. In that case, the momentum that the mirror absorbs will be twice this much. Or you might have some black object over there. You send some light on it. It absorbs all of it. Then this will be the pressure acting on that. This will be equal to the pressure acting on that. Or it might be that you have some transparent object, like a glass. 80% of the wave you send just passes through. Well, that would mean the glass absorbs only 20% of this momentum. So the force acting on the glass will be just given by the 20% of this one. This is just the flow of momentum. So if you have a concrete case where you want to calculate the force, then you have to take into account how much of this is absorbed, how much of it is reflected back, how much of it just passes through.
Hocam bir sistemde şu mekanik momentum sıfır olma olasılığı var mı? Hani sadece elektromanyetik momentuma sahip olabiliriz.
Well, let's see. What is the electromagnetic momentum density? This was mu0 epsilon 0 E cross B. over mu 0.
The density.
This is the density. You see, what we had proven was this one, P mechanical plus mu 0, epsilon 0, dV, S. When we looked at the rate of change of this quantity, this was equal to minus dA I Tij. So this is what we had proven. So the integral over the volume of this quantity gives me the electromagnetic momentum. So we can identify this as the electromagnetic momentum density. So if we have, let's say, zero mechanical momentum, well, that would mean nothing is moving in my volume. So they are all at rest. Or not necessarily at rest. If I have many objects, one can be moving in this direction, the other one might be moving in this direction. Let's just take two charged objects. They are moving in opposite directions with the same momentum, but just in opposite directions. So the total mechanical momentum of this system is 0. I have charged objects. So in my system, I have an electric field. They are in motion. They will be creating a magnetic field, a B field. So this is a system which has zero mechanical momentum, non-zero electromagnetic momentum density. Now, the total mechanical electromagnetic momentum, what's the value of the total electromagnetic momentum? It might still be 0, I don't know. If you consider all of the volume, all of empty space, let's say, then the total mechanical momentum will still be 0. Just imagine this case. We know that total linear momentum is conserved. It should be conserved. I have one charged object at rest over here, another charged object at rest over here. Just for the sake of simplicity, let's assume that they are oppositely charged. And they have the same, they are identical, they are oppositely charged, the same mass, etc. So when I release my system, they will just move in opposite directions towards each other. Their mechanical moment, initially, the mechanical momentum is 0. Initially, they are at rest. B is 0, so there's no electromagnetic momentum. As they accelerate towards each other, still their mechanical momentum will remain 0, so the electromagnetic linear momentum should also remain 0. Of course, the electromagnetic momentum stored in all the universe remains 0. Okay, so let's start with waves. Eventually, we will be trying to identify electromagnetic waves in Maxwell's equations. But let's just review what you know about waves. You should have taken a course on waves last year, or more than 1 year ago, right? So what's a wave? Okay, a wave carries energy. But not everything that carries energy, we don't call everything that carries energy a wave. For example, wrong target. Well, that carried energy, but we don't call that a wave. You shouldn't sit next to Sergeant.
Wave can be defined as a volume of energy that moves.
Well, that was a volume of energy that moves. Right? A chalk, there's a volume, there's energy in that volume. So it's a volume of energy that moves.
Ama parçacıkların taşınmadı, sadece enerjinin taşınmadı.
Well, okay, that's good enough, let's say. So it's not the motion of particles, but it's the motion of energy, transfer of energy. Well, that separation gets kind of vague when you start doing quantum physics, but that's acceptable. Well, usually when we mean a wave, there is a quantity. It can be anything that you like. Like it can be the density of a medium, or it can be the height of the surface of the ocean. It can be the electromagnetic field, that's the magnitude of and the direction of the electromagnetic field. So you have some quantity. Just for simplicity, let's assume that quantity is, there is only one dimension in space. It changes in time, but as it changes in time, it will move. Well, you have all mentioned that it moves. It moves in such a way that its shape doesn't change. So, okay, that is one restricted definition of wave. For example, it can be, when we are talking about sound waves, we can describe it as a pressure wave, for example. When I'm talking to you, what happens is there's my vocal cords, they are just compressing the air by vibrating. They are just compressing the air nearby. And once you compress this air in this region, well, that air will be compressing the air in the next region. And so it will keep compressing the airs in successive regions. But then my vocal cord just moves back, releasing this compression. So there is just one part that is moving in this direction, which will be compressing. There is the other part of the wave, which is just releasing this pressure. And as this variation of pressure, in that case, F can be the change in the pressure in the atmosphere. And as the wave propagates, when I first create this wave, the pressure as a function of x and x might have such a shape. This is at t is equal to t0. My vocal cord compressed this region, and then it relaxed. So the pressure just increases as the air is being compressed, and then the pressure just drops as it is relaxed. But you see, this part of the air tries to pressurize this region, whereas the pressure in this region will be dropping. So at the next instant, I will have a higher pressure over here, lower pressure over here. And at the next instant, higher pressure over here, lower pressure over here. At a later time, this might look like this shape. The shape is more or less constant. It doesn't change. So if you just follow the waves in the sea, you will see that their shape is more or less constant until they reach the shore, at least. So their shape doesn't really change. This is more or less what we call a wave. Well, it's not strictly true. I mean, we will be talking about different medium. This is the wave in a linear medium, which is non-dispersive and non-dissipative. So what does each one we mean? Non-dissipative just means it doesn't lose energy as it is moving. Of course, all the waves just lose energy as they move in real life. But if you see waves in the ocean, in the open sea, you will see that they travel a huge amount of distance without their shape changing. So they don't really lose energy. But if you have a dissipative system, the wave will lose energy, so its amplitude will just get smaller and smaller. It is non-dispersive. Well, do you know the meaning of dispersion? The Turkish analog of dispersion. For example, when the police attacks the group of protesters, they are just dispersing the people. Yeah. A non-dispersive medium is a medium in which the waves do not change their shape. So if it starts with this shape, it will stay with this shape. Well, we will see that if you, in a non-dispersed, in any medium, if you send a wave of a given frequency, the frequency remains the same. And it will have a certain velocity in that medium. If all the frequencies move at the same speed, then the shape will not change. So that's what we call a non-dispersive medium. For us, the non-dispersive medium will just mean that the velocity of the wave is independent of the frequency. That is not necessarily the case. For example, for light, we will eventually see, when we study light in electromagnetic waves in medium, we will see that different frequencies behave differently in a given medium. So that is what we call a dispersive medium. Because of this dispersive property, we have phenomena like the rainbows. because different frequencies of electromagnetic wave, they will be refracted differently. So different frequency just means different colors, if we are talking about the visible spectrum. So different colors will just arrive at our eyes from different directions, and so we see all these rainbow colors. And what else? It was a linear medium. This is a linear wave. Linear means just that if you have two waves, for example, you can just send two waves to each other. They will just pass through, and after they just pass through, they will just have exactly the same shape. And as they are passing through, the total change in this quantity will be just the sum of the changes created by each one of those waves that you send. So let's see. Let's just call the peak point. Let's just define a function f of g of x. So this is our g of x. So just for simplicity, I just assume that the maximum of g appears at x is equal to 0. Now this, let's say, is at the point x0. And this is at the point x1. So what do we know? F of x0, t0. This is the value of f at this time, at this point. Since the shape is not changing, this should be equal to f of x1, t1, since the shape is not changing. But the shape is given by this function over here. This should be equal to g of 0. It depends on your medium. Some mediums are dispersive. Some mediums are dissipative. Some mediums are not. For example, in our case, we will be talking about electromagnetic waves. And for electromagnetic waves, the dispersion is caused by friction, by resistance, sorry. So if you send your wave in a region which can, in a medium where you can create currents, so the electromagnetic wave will transfer some of its energy to the motion of the electrons, or whatever are the charge carriers, but those electrons, if there is resistance, they will lose energy. So they cannot give its energy back to the electromagnetic wave, it's dissipated. So such regions, we will see that they are dissipative. You lose energy. If you cannot create currents, you can still heat the system if it absorbs that frequency. Thus, in that case, it won't be the electrons moving around, but the atoms, they can be excited by that frequency, for example. So they will absorb energy from your electromagnetic wave. And then not all that absorbed energy will go back to your wave. It will be, some of it will be converted into heat. And that is your dissipation. So if you want to learn whether a system is dissipative or not, you have to study what happens to the energy of the electromagnetic wave, what processes absorb that energy and send it to somewhere else, not to the electromagnetic wave. Now that we will continue. So this basically is the statement that the shape doesn't change as you move. Well, let's see. This wave we will give it a velocity v. So what we can say is, well, let's say at t equal to 0, it started from somewhere at some point. Let's choose that point to be our 0 point. Then x0 is nothing but v times t0. x1 is just v times t1. So basically, x minus vt is always 0. So this g of 0 is actually nothing but g of x0 minus v of t0, or g of x1 minus v of t1. Well, this basically tells me that f of xt is actually g of x minus vt. So if this is the case, since the shape is determined by g itself, the shape doesn't change. So at least one property is apparent from this definition of the wave, the wave form. G is called the wave form. Well, in fact, we don't have to have just waves moving in one direction. We can have waves moving in the other direction. And in general, any wave can be written as such a sum. So this is a wave. This is a wave moving in the x direction. And this is a wave moving in the minus y x direction. And this is the linearity. So if you have two waves, I mean, you can even have two waves moving in the plus x direction, so, and then the wave form, the shape of the wave will be just the sum of those two waves. Or you can have, just call all the waves moving in the plus direction as your g, all the waves moving in your minus direction as h. The sum is your system as a whole. And since we can sum them, this is what we call linearity. Well, not all waves are linear. For example, one commonly known wave is what's called the tsunami. They are nonlinear waves. Or when you have waves in ocean, when they are approaching the shore, they behave nonlinearly. You cannot describe it as a linear wave. Well, if the waves in a medium satisfy this relation, or if the fields in your medium satisfy this relation, then it's linear. Now, the concept of linear is just quite a general concept. If you have any two things that describes some system, if the sum also describes the same system, whether it might be a mathematical system, a physical system, whatever kind of system you can imagine, then that system is called linear. Well, basically, a linear wave is a linear medium is a more proper way of putting it. It's a property of the medium, not of the wave. A linear medium is a medium in which the waves, if you have two waves, two separate waves, then their sum is also a wave in the system. So, for example, I have a very long string. Okay, I have a wave solution that has this shape. This is one solution. I have another solution that has this shape. This is a completely different system, it's a different solution. It looks completely different. It can be a different time. It can be the identical but a different system. This might be one string, this might be another string. So I have these two solutions. A linear medium just tells me that this is also a solution. It's just the sum of those two. So this is what the linear means. So separately, I can create those waves separately, independent of each other, but I can also create both of them at the same time. This is the meaning of linear.
Lineer, yani sistemi incelerken bunu sinüs kosinüs dercesinden yazıp hani birbirine toplama çıkarma yapabiliyoruz aynı zamanda değil mi?
Well, that is what we will come next.
Peki non-lineer olduğunda hani bunlar sadece higher order mı oluyor yoksa başka bir farklılık mı var?
Well, depends.
Tamam.
Yeah, there are approximation methods which will tell you that, okay, they can be this nonlinearity, the effects of nonlinearity can be treated as higher order corrections, or those corrections might not be small, so you cannot really call them small corrections. Then you have to find different approach, which doesn't exist in general.
Tamam. Üçüncü olarak Fourier transformada gelecek miyiz?
Yes.
Tamam. Sonuçta lineer medium değil de non-lineer medium olsaydı medium yine tamam behavior'ı sistem non-lineer olmuş ya da hani medium non-lineer olmuş. Çoğunlukla aynı şekilde etkileyecekti değil mi?
Well, what we call the system is our medium.
Peki örnek verebilir misiniz non-lineer medium'u?
Well, let's see. We studied materials last semester, right? So we said that, okay, there is this polarization of the medium. And in fact, there also we discussed that, for example, if you have an electric field in the x direction, it might create a polarization in the y direction, depending on your medium. I mean, your medium need not be rotationally symmetric. And unless the x direction is kind of a special direction for such a system, an electric field in the x direction might create some polarization in the y direction. And they will be proportional to each other. Of course, an electric field in the y direction can also create a polarization in the y direction, or the electric field in the y direction, z direction can create a polarization in the z direction. Well, this epsilon is a tensor. So again, as I said, it just carries two-direction information. What is the direction of the applied electric field? What is the corresponding polarization? This is what's called a linear medium. Because it's linear because the polarization depends on the first power of the electric field. But of course, you can just think of this as a kind of a Taylor expansion. Pi, this is a function of the electric field. And if it is not ferroelectric, when the electric field is zero, the polarization should be zero. Or if that is the case, then if you just make a Taylor expansion of this thing, you have the Pi with respect to Ej times Ej. This is the linear term, plus del Pi with respect to Ej, Ek. Then you have Ej, Ek over 2, plus the other terms. So those, in general, for a general medium, there's no reason for these terms to be absent. By the way, this is a rank 2 tensor over here. It carries two-direction information. This is a rank 3 tensor. It's just, I mean, some vector take its derivatives with respect to two other vectors, basically. Those are the nonlinearities. Now, this term might be small, but no matter how small, I have the product of two electric fields. For a sufficiently strong electric field, this term might be as important as this term. So in fact, for any medium, it becomes nonlinear for sufficiently strong fields. Well, of course, this sufficiently strong, for some mediums, it will be even a moderate electric field is sufficiently strong, because this derivative for that medium is not small. For some medium, that sufficient electric field is not an electric field that we can create in the lab. And you have all the spectrum in between. It's a property of the medium. For example, one of the nonlinear dielectrics we have basically conductors. Polarization is not just the electric field multiplied by the number. And for conductors, we have different treatments.
In our wave function, we wrote went from plus x variation minus x variation. We wrote E as a velocity. Necessary to have the same velocity.
We will see. Well, this is a non-dispersive medium, what we are writing over here, meaning that the velocity is the same for all frequencies. We will also see cases where we have a dispersive medium where different frequencies might have different velocities. It is possible, but I mean, we start from the basics and then eventually build up to the more complicated. The simplest wave you can think of is V is constant. Okay, he said wave function and then you just came up with quantum mechanics. Okay, that is for the break. Okay, we will be giving a break in a couple of minutes. That is for the break. So let's stick with electromagnetism for the time being. Okay, any questions? Other questions? That's the definition of linear. So if we have a linear medium and you have any two solutions, their sum is again a solution. Okay, let's go for a 10-minute break and then we can continue. And you can ask your wave function collapse question now.